Hello everyone, thank you for coming. Welcome to the next session for Signal. This is advanced sampling, following on from the sampling talk that Simon Gray did a couple of weeks ago. I'm going to be using version 7.05, which is the very latest one available for download on the website. There will be a 7.06 coming out hopefully next week. Keep an eye out for that. I'm going to start by talking a little about arbitrary waveform outputs. If we, in the sampling configuration, looking at the outputs tab here with pulses output, I've got enabled one DAC. If I go into configure pulses, you notice this bottom left-hand corner, we have an icon for arbitrary waveforms. And we can drag that up onto the DACs here. When we drop it, we get a rectangle appears indicating that there is space there now for an arbitrary waveform output. Now the question is at what arbitrary where we're going to get this arbitrary waveform from. And the way to do that, if I just come out of here, I can open a data file. Let me some of the standard files that are available when you install Signal. File. Okay, so this file has got some action potentials in it. Our complex draw mode, let me simplify that. The standard display. And I don't need a virtual channel, so I can get that. Memory channels, okay. And supposing I want to output these action potentials, what I can do is zoom in on them. And getting the section of waveform that I want to output, I can then just right click and say copy, or do a Control-C to add that to the clipboard. That's copied as floating point numbers. So this is scaled to sort of roughly between -50 and 25. They happen to be millivolts here, but the units will be ignored when we come to use this. So when I go back into the sampling configuration, we want the DAC scaling to correspond to the waveform we're going to output. So let's put that in at say 50 millivolts. And when I draw into configure pulses, and the arbitrary waveform goes here. Now I can right click on the rectangle there and say paste. And we get a dialog saying what do we want to do with the waveforms in the clipboard. It tells us a little bit about what is in the clipboard, how many points we have, what sampling rate it was sampled, each duration. Now we've only got one channel in here, so we only want the first channel in the clipboard. We want to use all of the data in the clipboard, so we don't really need to use the offset there. So we're only modifying one output starting on DAC 0. We could have had multiple channels of output had we had more than one channel displayed here. And this is going to tell us how many points we're going to overwrite in the clipboard starting at a particular offset for the arbitrary waveform. So we're automatically adjusting the length of the output to the length of the data that we pay. Sorry about that, and I think we, the wrong button got hit somewhere. Yeah, we're where we're going to automatically adjust the frequency at which the waveform is played out to match the frequency at which it was sampled, so that it's maintained in real time. And I say OK. You can see the waveform turns up in the upper part of the dialog here. So now when this pulse configuration is run, this waveform will be output on DAC 0. We can try that and just check that I am sampling. I've got DAC 0 connected to ADC 1 at the moment. So let's, what happens when we run that? Turn the trigger off. And there it comes. So we're outputting that waveform. Now this is all very well if you've got the waveform exactly how you want it to play out already. You've already sampled the waveform that you want to replay on the DAC. But you may want to construct a waveform from scratch. And there are various ways to do this. You could create a memory view and use a script to build in memory a waveform using mathematical functions available in the script. Or we can use a virtual channel. Show you how to use a virtual channel here. So we've got at the moment, we've just got a blank line, a flat line at the bottom here for the virtual channel, and we can use the wizard, clicking on the button at the end, and generate waveforms. And for instance, generate a sinusoid waveform. Let's output this at 10 Hertz waveform. And starting at 0. So there's a simple waveform. If I show the whole x-axis, we can see what's happening. Now, the problem with playing out, this is using auditory experiments quite a bit for playing tones. The problem with a simple sine wave like this is at the start and end of the output, you tend to get a clicking noise as you introduce new frequencies when the waveform starts and stops. And so generally people, what they would want is a nice smooth beginning where the amplitude of the sine wave ramps up over the first X amount of time and then holds constant and then ramps down again at the end. And we can do that in a virtual channel by applying an envelope. Now an envelope basically is, it ramps up linearly and then holds steady the value of 1 and then ramps back down to 0 at the end. And if I multiply the sine wave I've generated by an envelope function, which again I can generate with the wizard, envelope, and we get a ramp up time. It's saying here all times are in milliseconds because I've chosen to use milliseconds in the preferences. So a rise time of, say, 200 milliseconds and a hold time of, let's hold that for 1600 milliseconds. And a fall time of 200 milliseconds. And we'll start the envelope at 0 milliseconds. Okay. And now you can see the waveform has a nice smooth beginning and then gradually ramps up to the full amplitude before ramping down again at the end. And that will avoid the annoying clicks that you can get when you just play a straight sine wave out. So having built that in there, I can double click on there to make it the only waveform there, copy that, go into the sampling configuration, and the outputs. And the DAC scaling, we need to adjust it here. And configure the pulses and paste into that one. And I get the same dialogue, same. And so there we have the arbitrary waveform with the nice smooth ramp up and ramp down into a sine wave output that you might want to use in your experiment. As well as building it either in a virtual channel or in a memory view, or even just in an array, in a script, if you preferred to build your data in another package, you could do that and then import your data into Signal and use it from there. I'd like to elaborate a little on protocols, which is a method of state sequencing. Look again at sampling configuration. We've got multiple states sampling. We get the states tab appears. Now, in the last sampling talk, we went into quite some detail about the different methods of ordering here. Protocol is probably the most precise way of specifying how you want to order your states. It can be arbitrarily complex, almost. If we go to protocols, now I've only got 2 extra states here. I can increase that maybe. 4 extra states. That's in addition to state 0. State 0, I should say, is you would normally set state 0 such that it did not produce any stimulus, because this is the state 0 is the state that is your fallback state when you finish stimulating and you just want to monitor. You would, by default, you fall back to state 0. So in the protocols, we can give the protocols names. And we have a whole set of checkboxes now. Create a toolbar button for the protocol. So when we're sampling, we can have a button on the toolbar at the top, which tells Signal to run this particular protocol, which can be very useful. You can actually switch between protocols whilst you're sampling. It will just finish the current sweep, the current frame, and then start the next protocol that you've clicked for. Do we want to run automatically at the start of sampling, or do you want to wait for the user to click on the button to say, right, start that protocol running? Do you want to cycle to protocol states? So do you want, if you're not writing to disk, do you want the state sequence to continue to execute? Or do you want it to hold on the current state that you're on? So if you want it to hold on the current state you're on, you would check that box, and it would not continue to execute the protocol if you're not writing to disk. Use steps per cycle, per step write flags. You notice it's got these check boxes underneath the right column down the side here. So if we turn that on, these are now enabled such that you can specify that any particular step in your protocol you don't want to write to disk, or you do want to write to disk only for that particular step. Saves you using up space on things which are perhaps just there to pad out the time, or just to monitor things whilst during the experiment. You can turn on the writing to disk at the protocol start. If you want to do that, then you can't have your write first step as an enable, because the two could be conflicting. I mean, you don't want the ambiguity. So, and reset pulse steps at protocol start. If you've been perhaps executing a state where there's an increment in either the duration or amplitude of your pulses for that particular state. The question is now, do you want that increment to be reset when you start your protocol, or do you want it to carry on where it left off? For simplicity, you probably want to have a reset, but there may conceivably be instances where you don't want to do that and you just carry on with whatever amplitude or duration you've reached in your increments. So the steps themselves, you specify what state you want to execute, how many repeats of that state you want to make, and then what the next step you want to execute is. Usually, it starts off going down 10 repeats of state 2, and into the next one. And of course, you can step backwards if you want. So if you only wanted to do 10 repeats of state 2, and then go back and just do 1 of state 1, you could have your next step as state 1. So you didn't just run around in a loop executing that particular pattern. Similarly, you could also keep going and use up all your steps, doing different states for different numbers of times in a very specific way. What you can't do is jump to a random step. So randomization is better done by other methods. You could, if you had a reasonably limited number of steps you wanted to randomize them in advance, and then type your order in at this point, or use a script to insert them. That would give you a repeatable order. Obviously, you only do 10 steps with that, but it is actually possible to chain protocols together. So having executed one protocol, you could jump to the next protocol and have much more complexity over the course of the experiment that way. So, do we want to repeat the entire protocol once? If we reach a next step and we want to finish, we can set the next step to 0, and that will terminate the protocol. And the question is, what do you want to do then? Well, you can repeat the entire protocol by inserting a value here. So if you want to do it twice instead of just once, you put the 2 in there. And having completed your protocol, we can either finish, in which case it will drop back to state 0 and just idle, or we can jump to another protocol. Now, normally we've only got one protocol defined, but I can add another protocol. Give it a meaningful name so we know what they are on the toolbar. So now we've got name doesn't become active until becoming active until I select another one. Yeah, having completed the first, I then go to the second. And I could go around in a loop and say, having completed the second, I could then jump back to the first, or I could just finish. And again, what do we want to do when the protocol finishes? Do we want to drop back to state 0, or just turn off writing to disk and stay in the same state? You can see you get quite a as complex as you like, really, the ordering of your states by that method. So your sequence of stimuli can be arbitrarily complicated. It's quite powerful. If I try to run that, okay. So you're seeing you've got now a protocols appearing on the sample control bar here, on the states bar. So when I'm sampling, I don't have anything particularly exciting in my states, but going through second protocol might not have any impact because it's not obvious what state. No, that it shows it here. I think they're all the same as state 2. But that's how you would select your protocols and make change protocols if you wanted to do that whilst you're sampling. Another area I wanted to talk about is sequences. If we look in the sampling configuration at the outputs, you notice you've got this setup type, and so far we've only really looked at pulses, which is the graphical method of defining what your outputs are going to look like, which has its limitations. For instance, in configuring graphically, there is no decision making available. You can't say only output this pulse if an analog channel is above a particular threshold, or you can't say wait for a particular threshold to be crossed before doing something. So it has its limitations. If you want to start getting into, if you find yourself hitting limits like that, you want to move on to sequencer control for your outputs. Sequence control is text-based. You essentially write a program which executes within the 1401 rather than within the PC. The advantage is obviously running a sequence inside the 1401 is that the timing is much more accurate. Windows is not a real-time operating system, so any timing done within Windows will be subject to some variation from random events like using the mouse or getting an email or something that would affect the timing of your program. Whereas if we run a sequence inside the 1401, the timing is locked to the clock of the 1401 and is therefore not subject to that variation. The period, the step period, so this is the amount of time taken to execute each instruction in a sequencer. Now, it's 1 by default, which for many purposes is enough. You can go quite a lot smaller than that, depending on your 1401 type. Certainly, you can take it down to 10 microseconds or less for sort of really new, more powerful 1401s. Maximize wave rates. If we're doing arbitrary waveform outputs, we may be limited as to how fast we can play that waveform out. And we can slightly improve on the limitation of the waveform output by checking this box. That has a slight penalty in that the timing accuracy of the waveform output may be slightly influenced. So you don't use that if you really have to, and then you do some careful checking to make sure it was still within your limits, your specifications limits. Free run without restarts. So your sequence, if you're using pulse outputs, your sequence, the outputs start at the beginning of the frame. And that's also true with sequence outputs. You can have your sequence of instructions which begins executing at the start of the frame. So it's reset essentially every frame. Now, if you can free run without restarts, then the sequence continues to execute even if you're not sampling within your frame. That's particularly useful if you're waiting for some particular event to happen before you start sampling, you can use the sequencer to trigger the sampling. So you can have almost arbitrarily complex criteria for starting your sweep, starting the sampling of the frame by using a sequencer with a free running, so that it's running all the time and monitoring the inputs all the time. The sequencer, it's possible to cause the sequencer to jump to certain points within its execution. You can do that by setting it up so that it can be controlled by various other means. So we can have only if you press a key on the keyboard or a button on the control panel, which will appear at the top of the screen when you're running your experiment, or only through the control panel, so the keyboard isn't allowed to affect the behavior of the sequence. It can be useful if you've got, if you do perhaps doing your subject you're working with has access to the keyboard. You don't want them to actually cause the sequencer to jump around. Or you can set it so that only the script can send commands to the sequencer to affect its behavior. And on this side, we've got the DAX. We've got DAX scaling again. You only have one set of DAX scaling values. So it's very similar to how you have for pulses, but it affects all the DAX. So full scale, I'm going to say is going to be 50 millivolts in this case. And the waveform areas, so you can got arbitrary waveform output. How many of them do you want to be there for use with the sequencer? And how many points do you want in it? And at what rate do you want an arbitrary waveform to be played out? The digital outputs are always enabled within the sequencer. You can access them directly from the commands. The DAX you have to enable within the checkboxes before you can use them within your sequencer. And if I open these example sequences which are supplied with Signal, I'm called My First, and if I go open that separately, we can actually have a look at what a sequencer looks like. So we got, these are quite low-level instructions, as you can see. They're doing pretty basic things. We have a set of variables available within the sequencer. By default, they're named V1 to V64, and they can have values assigned to them. These are 32-bit integer variables. It's the only type of variable available in the sequencer. So you can't do floating point arithmetic within your sequencer. You will have to work with integers. We have a delay instruction, and it does exactly what you expect. It just stops the sequencer for an amount of time. And this is the amount of time it is in sequencer steps or sequencer ticks. Now by default, this is 1 millisecond. So this is going to stop for 248 milliseconds in this case, because we've set the sequencer tick size to be 1 millisecond. Not forgetting that the instruction itself takes a millisecond as well. So this is actually stopping for 249 milliseconds, not the 248 that you might expect from the number there. We've got a simple instruction to set a value on the DAC. So DAC 0 to 2 volts or 2, we're working in millivolts, so we're assuming that the DAC scaling is correct for whatever amplifier we're connected to, whatever device. Another delay, another value on the DAC, set the DAC down to 0, another delay. And then we got this instruction which is used a lot for looping within sequences. That's dBnz, it's decrement and branch if not 0. So it's going to decrement the value in variable 1, which has been initialized to a value of 10, so that drop to 9, and the result is not 0, so it's going to jump to the label LP, which is the label we've inserted here, marked with just the start of the line with a colon after it. So this is going to run around this loop, decrementing V1 each time until V1 reaches 0, at which point you're going to run to the next instruction, which just halts the sequence. And I should also say we can have comments. I would very much recommend you use them if you're writing sequences, just to know what on earth is going on, as you imagine, because the commands themselves are very, very basic. To try and work out what the sequence is doing just by looking at the commands can be quite tricky, especially if you've got quite a complex and long sequence. So insert your comments so you know what's happening. We've also got this sort of greater than sign on the end of the comment with a bit of text after that. When you're executing the sequence, the control bar for the sequence will appear up at the top of the screen, and that will have text in it, which is the text that you're given here, so that the person using the program knows what the sequence is doing. Give you a few clues as to what you need to do. On the bar at the top here, we've got ways of jumping to particular labels within the sequencer, just as a navigation aid when you're editing, or keys. Keys we'll come on to in a moment. But keys are, you can specify a key press within your sequencer you want to jump to in the editor by selecting it in this list here. There's some other buttons are check, so it checks the syntax to make sure you haven't made a mistake. It's not found an error there. If I deliberately introduce an error and then check it again, unknown command, so it highlights where it's not going to work. It also tidy code, so if you put spaces in here and it's not lined up, it can be a bit tricky to see what's going on. You can just tidy it up with a single key press. It all jumps into place. And tidy with numbers, just to give you some line numbers, so you get an idea of how many instructions you've used and where, because obviously the timing of this loop, you'd have to add up the number of instructions in the loop to know how long that takes, in addition to adding on the delays, the extra delays from the delay instructions. And also make current, that means you want to put this sequencer, this sequence into the sampling configuration, and then it appears down at the bottom there. You can obviously go load sequences separately. You don't have to open them for editing. You can just browse for them and open them that way. And if I run with that, just check. Don't free run it. Basic. 2 ports. Okay, so DAC0 is connected to ADC1. And if I start, get trigger off. Okay, there's the output suddenly appearing down the bottom there, just so we can see it. And it resets it and reruns each time we have a new sweep. So if we look at another example that's included with Signal. Here we see there's a few other concepts being brought into play. The variables can have aliases. So when we can declare an alias at the top of our sequencer here. So V1 we're going to call fast. We can subsequently use the word fast within our sequencer to mean variable V1. We're using a macro ms, which is milliseconds. So ms with 8 means 8 milliseconds. So the macro knows what sequencer rate you set, so knows how many sequencer steps 8 milliseconds corresponds to. So we'll replace that when it comes to compile this, replace that with however many steps are required to generate 8 milliseconds. And we've taken a 1 off because we want to take into account the time taken for the delay instruction as well. So, and we've got 8 milliseconds or 99 milliseconds for fast and slow, as we call this variable slow, and amp, the variable name we've introduced as an alias for V3, which is the amplitude. We've got a new macro here, VDAC32. If you're setting the DAC using a number you type in, then the DAC scaling comes into play, and you can type a number in whatever units you define for that DAC. If you're using a variable, then you're into a different scenario. It's not just a case of the integer stored in the variable is the amplitude you want to output. It's what we've done is say we spread out all the possible values for a 32-bit integer over the range of the DAC. So to output minus 5 volts on a 5 volt 1401, the variable will need to contain 2 to the power 31 or minus 2 to the power 31 for minus 5 volts. And rather than having to work out what value of integer corresponds to what voltage on the DAC, we have a macro that does it for you. So that takes it knows what the DAC scaling is. It knows you want 2, in this case, millivolts. And so that will generate whatever value is needed for that variable, for that amplitude. There are a few other macros that you can look at. If I need help, I do an F1. You can see these are the various instructions here, various macros that can be defined to help you without, say, you're only having to do some quite lengthy arithmetic to work out what the integer scaling is. So move I is to move an integer into a variable. So we're moving the value of 7 into fast, and we're moving that is a very big number into the amplitude. And you can see the sequence instructions have got 2 sections, and these are keyboard controlled. So we've got this apostrophe F, which means if you press capital F whilst you're sampling, the sequencer will jump to that instruction. And apostrophe S, so if you type capital S whilst you're sampling, the sequencer will jump to that instruction. And essentially we're setting the DAC to 0, we're delaying by an amount. We've got a NOP. A NOP is no operation. So that's a way of delaying by 1 step. It doesn't actually do anything, but it does take whatever the step size is to execute it. And then we set the DAC back to 0, delay again, and jump back to the label FL, which we defined up here. And we do something very similar for the slow, if you press S, but this time the delays are longer. And we jump back to SL, the slow one. So it's a different loop. And it will stay in that loop until you press a key to make it jump out, or you reach the end of the frame. Or if it's a free running script, it will stay in that loop even if at the end of the frame. It will carry on running whilst you're not sampling, and then it will still be running when you start the next frame. So if I make that one current, let me look in the sampling configuration. And if you look in the sampling configuration here, we've got, let's sample for 10,000 milliseconds, so we've got 10-second frames. Should be enough to demonstrate the phenomenon. And okay, sorry about that. We had a power failure. Sorted that now. Can I just check? Can people see my screen? Can somebody ask me, put in the chat whether my screen is visible to them? Yep, you can see me. You see my screen? Yep, cool. Right. Okay, where was I? Yes, we've it's visible in the. We're all ready to go. So if we run. Now DAC 0 is connected to ADC1, so it should appear down here. Off. Okay, so that's coming in fast. I click on S, it should go slow. I click on F, go fast again, and slow. And that started the sequence again at the start of the next frame. So if I just import that second and look in this sampling configuration, if we run it rather than starting again at the start of the next frame. Okay, so it's fast, and it's slow. And at the start of the next frame, it's still running the slow part. I can also use the keyboard, so I do Shift F to go slow, and Shift. So it's Shift F to go fast and Shift S to go slow. I can switch between the two quite happily like that. Now, this is all it's all very simple. We have a rather more sophisticated example, which has been in play for quite a while. If I open this particular script, this is a script that not only interacts with the sequence, it does more than that. It writes the sequence before it begins to run. So based on parameters which you define at the start of the script, it will write an appropriate script for those parameters. And then when you come to sample, it will use the sequence in which it's written within the script, within the sampling. You see down here, here it's writing out lots of print statements to writing out scripts. You can see various parameters being inserted at this stage. And just to show you briefly what it does, what it's doing is it's waiting, it's measuring the baseline. These are for triggering stimulators of various types, electrical stimulators and magnetic stimulator there. You say OK, and what it's going to do is monitoring, even before I start sampling, it's monitoring the ADC input to get an idea of what the baseline activity is. That data can now be handed back to the script before I've started sampling. So the script can then perform some analysis on the data to work out what the mean level is and its standard deviation, from which it can then decide whereabouts to put the threshold that needs to be crossed before it produces some stimuli. And So that, having worked that out, it can then pass that information back to the sequencer to set a variable within the sequencer, which can be used for to allow the sequencer to know when to generate the stimuli. Now, more than that, we transfer some waveforms into the 1401, and we can play those waveforms out on the DAC. We're using those to give an auditory information to the subject. And in this case, it's going to tell them to get ready and then to go. The basic experiment originally was that when they're told to go, they'd be holding a ball. They drop the ball, it measures the EMG, and if the EMG crosses the threshold, then the sequencer will provide stimuli electrically and magnetically. So if I say fire, somebody to be ready.
Ready. Go.
And I'm simulating the EMG here with just a joystick, just rather than putting electrodes on. It then has to produce some processing on the data that's captured, and you can see the different codes which correspond to the different digital outputs that we've provided for stimulating triggering the stimulators.
Ready. Go.
It's like problems with the volume on the speaker. We're plugging the DAC in through an amplifier onto the speaker, and there we go. So if you actually look at what the sequencer is doing, we can open the window. Right one. Not there. There we go. This is this is what the sequencer looks like. You can see it's a little bit longer than the ones we looked at before. Similar in other respects. One of the things we got here, we've got a lot more variables. Again, these have been given aliases so that we can refer to them and know what they actually mean, more meaningful names to use within the sequencer. We're using a table. So we've only got 64 variables, and we want a table of values, which is going to be way more than 64 numbers. So this is like defining an array to use within the script. And the table is just an array, and you define how big you want that array to be. The table can be transferred directly to and from the sequencer by the script. So we're taking the DAC, we're moving values into variables. Chan command is looking at an ADC. So we're looking at the value on channel 1 of that we're sampling with the ADC. And set put a value from the table into the variable, and add 1 to that. There's not BLT, I should say, is not the type of sandwich. This is branch if less than. So if we got the variable's got less than a particular value here, then you go back to LL. So we're going around this loop and basically filling the table with values that we've measured on the channel, ready to pass them back to the script. And generates a marker on in the digital marker channel that we're sampling. Wave 1, that means we output the waveform that's been defined within the script and transferred to the 1401. So we're just going to play that waveform out. And this is where it says ready. Setting the DACs, generate another marker so we know where we are, and then play go, which is going to be the second waveform that we've transferred to play out on the DAC. The delay here will be a random number. Now the random number will have been generated within the script and transferred to the sequencer in advance, so that the sequencer can then make a random delay without having to generate its own random number. The digital out, so we got 1 digit per output, per digital output. We're setting them all to 0 except for the one in the middle there. That's the output 0, 1, 2, digital output 1. And trig means trigger the sweep, trigger the frame within Signal. So we're going to start sampling at this point. And set the DACs. And ticks, we're going to count. What we can do, you can press F1 at any time if you don't know what a particular instruction does. So if I press F1 on ticks, it tells me what the instruction does. So it tells me if I convert a number of ticks into a variable count. So it knows how many. It can execute an expression and convert that into a number of sequencer ticks for me. And we have a branch of greater than. And also this means if we're exceeding the threshold. So this is what we're doing here. We're looking for the threshold crossing, and if it exceeds the threshold, we jump down to another area. And there's more digital outputs and markers being generated at this point in the sequencer. If we look at what the script was doing in all this time, find the script. You see some various instructions going on in here. That's just setting up the sampling ready. Try and find the parts of the script. So we're setting up the waveforms, sample seek wave, setting up the waveforms in the 471 memory, ready for output by the sequencer. And if we look down, we can find putting some values in the user variables. This is not really related to the sequencer. And okay, so fire. This is when we start talking to the sequencer. And see, we're monitoring a sequencer variable. Sample seek var is looking at sequencer variable number 5 and looking for that changing. So when that's whilst this is not equal to 1, do yield and when. So he's sitting here waiting for this variable to be assigned to the value of 1. So we're basically waiting for the sequencer to be ready for us. And this is how the sequencer is communicating with the script, just by setting a variable number which we're watching for. Sample seek table, so we're going to extract the values from the table that are being put there by the sequencer using the sample seek table instruction. And then we do some arithmetic on them, calculating the mean and standard deviation. Having done that, we set the horizontal cursor. And we convert the value that's calculated for the threshold that we're going to set back into a value that's going to be suitable for putting in a variable in the sequencer. And we use sample seek var again, this time to assign variable number 1. We can't use the alias names defined in the sequencer to within the script here, because the script doesn't know what alias names we've used in the sequencer. We have to use the variable numbers. Sample key is the same as pressing a key on the keyboard, but because we've got a sequencer which has in it some keyboards identified, some keyboard triggers, then using sample key in the script will also cause the sequencer to jump to that value. So here's the T in the sequencer. With sample key T in the script is executed, it jumps to this point in the sequencer. And in this case, we're going to tell the subject to be ready. Yeah, and then everything else is the same sort of thing. We're using sample seek table again here to transfer values in, having worked out when we want to provide stimuli. So we can use the sample seek table to transfer tables or arrays of values either to or from the sequencer and the script. And equally, we can use sample seek var to either assign or read values of sequencer variables from between the script and the sequencer. Now we're a little short on time for going into dynamic clamp, which is a whole other area of advanced sampling that I was going to get onto. I should very briefly just mention that it does exist. It's something you would use in current clamp mode. I have to set my DACs up. If you set the right correct scaling on the DACs and the inputs, you could then go in and create models, which are conductance models. Models will read the voltage, the cell membranes during a current clamp experiment, and inject current. That is, having read the voltage, it will know how much current to inject, given a particular formula for that. I think we're about out of time now. So if anybody has any questions, then do please let me know. I'm quite happy to. Yeah, I could say that while we're waiting for any questions, the models that we can add here, we can add multiple models, and the conductances which are injected by each model are added together. So we can have, for instance, you can have a leak and a Hodgkin-Huxley model at the same time. You can have some noise. And so on and so forth. Values that are invalid units, it'll actually check that you are actually injecting a current, and we've got the DACs at the moment. Close that. We've got the DACs scaled. Let's put it in pulses mode. I've got the DAC scaled in millivolts rather than picoamps, which is not going to like. Typically, you're going to have 2,000 picoamps on your DAC. And so the clamping is now a lot happier about the DAC. It's not so happy about the scaling on the analog channels. I could change the scaling on the analog channels, assuming this is picoamps on that channel, I think. And this is going to be millivolts. I think now it's going to be a lot happier. Certainly this part of the dialogue is a lot happier that all the units tally with doing current clamp. And it's not so happy in the input channel. Yeah, that's better. So the input has to be in millivolts and the DAC has to be in picoamps or nanoamps. It will it will adjust depending on the units, how much current it needs to inject. Would anybody here be interested in a dedicated dynamic clamping session? Yes, this is a very specialized area, and we're always wondering how many people actually use it. I know those that do, very appreciative of it. They're about the only game in town for certainly doing this commercially. It's very quiet on the chat. Okay, well, I'm always happy to receive any emails. You can send them to softhelp@ced.co.uk. Any questions? That we're about out of time, so I shall leave it there. Thank you all for coming. See you next time. We're going, I think we do have a patch camping session coming up as well in a week's time. Okay, thank you.